Hi, my name is Andrew Bukowitz, and this is my lab report for Physics 2012 at Georgia Tech Lab 5, Magnetic Braking. In this lab, we will collect data for the amount of time that it takes a magnet to fall through a conductive metal tube. The metal tube that we use is aluminum foil, and we do this in order to demonstrate current in Faraday's law. A few key concepts that are used in this law are Faraday's law, Lenz's law, the Biot-Savart law, Newton's second and third laws, and the time derivative of magnetic flux. And a few of those equations are shown on the right. So as mentioned, the main experiment of this lab is to drop a magnet through a conductive metal tube made of aluminum. A few measurements include the length of the tube, the width of the aluminum foil, inner radius, outer radius, the mass of the magnet, and the magnetic dipole moment of the magnet. From the 5 times that we dropped the magnet into the tube, we averaged the time that it took to fall through, and that average was 1.21 seconds. And then our final result from our computational model was a time of 1.3 seconds. A few checkpoint questions before we dive into the code and the model output. To start, number 1, why can't we use a ferrous tube, for example, a steel pipe? The reason that we can't use a ferrous tube is because ferrous tube contains iron, and iron may become an induced magnet, which would interfere with this experiment. Question 2 is what happens to the magnet? How does this compare to a magnet falling in free space without a tube? What happens to the magnet as it falls through the tube is there is a force exerted by the tube on the magnet that counteracts the gravitational force. And so the magnet falls much slower through the tube than it would if dropped outside of it. Here are a few snapshots from the computational model that I coded in GlowScript. To start, I created the bar magnet as an object and I visualized it in a graph. Next, I created the tube of aluminum foil and I added in some constants that we will use in our calculations. Finally, to close out some of the code from that model, I created a function to calculate the magnetic flux, and then I created the simulation loop, which when we start the simulation, it'll display the magnet falling down the tube and track its velocity on a side-by-side graph. Here's an excerpt from our model output. So what we see on the left is the tube modeled with the magnet inside of it with the red and blue forces shown next to it. And then we see the graph of velocity versus time on the right. And our computational model gives us a time of 1.3 seconds. So immediately we're going to kind of dive into a few discussion questions to help better understand what happened in this experiment. So question 1, the intensity of the color on the tube indicates the magnitude of the current flowing through each ring. Which color corresponds to clockwise current and which counterclockwise? So red corresponds to clockwise current and blue corresponds to counterclockwise current. And this is because these are the directions that current must be flowing in order to keep the magnet floating. Question 2, what happens to the dynamics of the system when we flip the magnet around? When we flip the magnet around, the currents would run in opposite directions, but the magnet would still experience the upward force due to the conductor. Next, how does the total time in tube of your real-world system compare to that of your computational system? So we saw just a slight difference between our computational time of 1.3 seconds and actual time of 1.21 seconds. And the ways that we could have made this difference a little bit lesser is we could have accounted for air resistance in our model, and we could have modeled the tube better with more smaller rings. Question 4, what does the shape of the velocity versus time plot tell us? So when looking at that graph, we see initially that the velocity steadily decreases, but then the conductor becomes charged, and then the forces sort of even out for a period of time, and then velocity then decreases after it exits the tube. See some final questions. What if the resistivity of the conductor was reduced as close as possible to 0? So if this were to happen, the force holding up the magnet would continually increase. and would continue to decrease over time to the point that the magnet would stop falling because the force would be equal to the force of gravity. Next, what if holes or slots were cut into the tube? So if holes or slots were cut into the tube, those holes would interrupt the flow of current through each of the rings. And so the total current flowing through the rings would decrease, and this would decrease the forces upholding the magnet.